Example 16.5, testing the loop pattern, is on page 596. It has a picture like you see here. It says use the loop pattern to predict the potential difference between point A and point B in the electrical circuit shown in the figure. So in order to predict that, you have to use the loop pattern to determine the current. You can see the direction that current is. Assume that wires and batteries have negligible or zero resistance compared to that of resistors. To determine the direction of the current, note that the 10-volt battery is going to have a larger EMF than the 4-volt battery. Therefore, the current in the circuit will be clockwise. The batteries are sort of opposing each other the way that they're set up, but the 10-volt battery is going to have a greater push. If we go clockwise from A, we would have, well, we've got the change in voltage of the 10-volt battery plus the change in voltage of the 20 ohm resistor plus the change in voltage of the 4-volt battery plus the change in voltage of the 60 ohm resistor plus the change in voltage of the 40 ohm resistor. All those have to be equal to 0. The change in voltage for the batteries is easy. It's their voltage value. The resistors, you have to use Ohm's law. Think about Ohm's law a little bit to figure out what the voltage would be. Reminding you that Ohm's law, current I equals change in voltage over the resistance. Well, if we want to know change in voltage, that would be this. Change in voltage equals current times resistance. So for each of the resistors, this is what we're putting in. And if we're talking about the change in voltage of a resistor going in basically downstream of the current, it's going to be negative IR. So our change in voltage for our 10 volt, that's just positive 10 volts. Change in voltage for that 20 ohm resistor is, and I'm going to put some brackets in instead. Oh no, maybe not. I'll just make that into a bracket. Negative I times 20 ohms. Current, resistance. Okay. Change in voltage across that 4-volt battery. Notice with the first battery, it is going downstream of the current like it should be. I have it as positive value. This battery is going opposite. The current is coming in. And remember, we're thinking of current as positive charges are coming into the positive side and going out the negative side. That's not what they would like to do normally, but they have such a push from this 10-volt battery that they are. So this is going to be negative 4 volts because it's kind of going backwards through what we'd expect from that 4-volt battery. Our 60 ohm resistor, negative current, we don't know what the current is quite yet, times 60 ohms. And the 40 ohm battery, negative current times 40 ohms. All those values, those voltage loops, have to be equal to 0. You got to combine like terms because we're going to be trying to solve for I. Send the page down a little bit. So on the left side, we're going to end up with a positive 10 volts minus 4 volts. All the I values we're going to want to move to the right. So they were negative I's, but now we move them to the right side. There'd be positive I's. You'd have to add I 20 ohms to both sides to get to the other side. So now we've got I times 20 ohms plus I times 60 ohms plus I times 40 ohms. Ooh, that's a nasty omega. There we go. Now we're going to want to factor out your I value, and what you're factoring out are those ohmic values. 20 60, 40 ohms. Those have to be equal to, we can probably do this now, 10 minus 4 is 6 volts. If we want to get the current by itself, we would divide everything that we have on this side is over there. We could even combine these values if we wanted to. 20 plus 40 plus 60 is going to be 120 ohms. 120 ohms. So now this and this cancels. You end up getting a value for your current being equal to 0.050 amps. Now that we know the current, we can look at the voltage drop from point A to point B, because now we know the voltage, we know the resistance, we know the current. We didn't know the current before, that's why we had to solve for it. So from point A to point B in the clockwise direction, so just going from A straight shot to B, it's going to look like this. The change in voltage, I might even start this in a different color. Change in voltage from point A to point B has to be equal to change in voltage across that 10 volt battery plus the change in voltage across that 20 ohm resistor. Change in voltage across that battery was just 10 volts, positive 10 volts, in the direction that the battery is pushing it. And remember, V equals IR, change in voltage equals IR. Since it's going across the resistor in a downstream pattern, we're going to call that negative 0.050 amps times 20 ohms. If you take this value, multiply them together, 10 volts, negative 1 volt, that means your change in voltage from A to B is going to be a positive 9 volts. You can do it the other way. You can go counterclockwise, starting at A, flipping around down through these two resistors, through the battery, back to B, through the smaller battery, basically going against the current. The rules still work, just the same. So now if I say from A to B, so let me clarify that this was going from A directly to B and just had to go across the battery and the resistor. The second way to do it, change in voltage from A to B, is in a clockwise pattern, counterclockwise pattern, excuse me. And that's going to involve a battery and two resistors. So, change in voltage from A to B is going to be that change in voltage across the 40 ohm resistor plus the change in voltage across the 60 ohm resistor plus the change in voltage across that 4 volt battery that is essentially mounted backwards. It's the positive current flowing this way. It has to flow through a battery that is mounted backwards. Although we can do our math against the current, there's no reason we can't. So, since we're going against the current now, we no longer call this negative IR, we just call it positive IR. So, a positive 0.050 amps times 40 ohms plus a positive 0.0, oh, that's supposed to be a 5. Boy, I have never seen a 5 that looks like that. 60 ohms plus, now that we're talking about going in this pattern, if we were going in that direction, our 4-volt battery really wouldn't be backwards. So we're going to give that as positive value as well. Add these together, or multiply these together. This comes to be 2 volts plus 3 volts plus 4 volts. Gives you an answer of 9 volts. It's positive 9 volts. Either way you go, from A to B, whether we go clockwise or counterclockwise. So the big take-home message, Kirchhoff's loop rule, is that the sum of any loop, the sum of the change in voltage, has to be equal to 0.